Hello everyone and welcome to this presentation. My name is Joanna Luberacka and I have recently been working as research intern at Jacoti. One of the main products of Jacoti is a hearing diagnostic smartphone application called Jacoti Hearing Center. Anyone with an iPhone and appropriate earpods can download the app for free and test their hearing at home without going to a hearing professional. Today I will tell you about a study which we did using audiological data collected by this app. Let's start with an introduction. Smartphone-based audiometry, like the Jacoti Hearing Center, allows for performing a hearing test when there is no direct access to a clinical audiologist. This might be a practical solution in less privileged societies, but is also important in all countries to minimize the contacts between patients and healthcare providers in the times of a global pandemic. However, there are several potential limitations of a test performed at home with a smartphone. In contrast to the clinical test, it does not ensure the acoustically treated room or specially dedicated equipment like audiometer or calibrated headphones. There is also no specialist who controls the procedure. Therefore, smartphone-based diagnostics has to implement various solutions to compensate for these factors. In Jacoti Hearing Center, the professional assistance is substituted with a detailed instruction and requirement screen. The role of audiometer is taken by a user-friendly automated procedure called duoton. And duoton is a patented procedure in which audiometry thresholds are measured in pairs using a continuous tone stimuli for one frequency and a burst of short tones for the other frequency. And the application also warns user about using appropriate headphones. And to ensure the possibly quiet test environment, the inbuilt noise monitoring system is used. Despite all these solutions, the question if smartphone-based audiometry is a valid diagnostic tool is still openly discussed. Now, how could we evaluate this? Although smartphones are still relatively new, the automatic audiometry has been there for a long time and there are some established ways of assessing the overall quality of an automated test. On one hand, we can measure the accuracy by comparing thresholds obtained with automated audiometry with thresholds from conventional clinical audiometry, both under the same conditions. On the other hand, we can measure the reliability or robustness of the method by checking how consistent are the obtained thresholds between the two different test runs. And this is what we call the test-retest reliability, and this is the main object of the study that I am presenting here today. There are already several studies measuring test-retest reliability of smartphone audiometry under controlled conditions. This means audiograms were typically measured in soundproof booth using calibrated headphones under the experimenter's assistance. The results of such studies are promising and therefore we wanted to go one step further and analyze the test-retest reliability of a smartphone app in real-life conditions that are actually intended for this type of apps. And thanks to Jacoti database, which contains measurements performed by real users of this app, we were able to approach this question. However, as you might imagine, the audiological data collected by a smartphone app has its own nature. The advantage is having access to thousands of audiometry sessions from various iOS users worldwide. Such a population is rarely available for clinical studies. But there are also challenges. Even with the noise monitoring system, the app cannot fully control for the acoustic environment or for the attitude of the users. Patients can abort the test at any point or engage in another task simultaneously. Another very important aspect is that the range of measurable threshold values is limited, which we call the bottom or ceiling effect. At the bottom, the range of measurable values is limited because it's not possible to precisely measure how very low thresholds in the ambient noise. And at the other end of the scale, we have the device output power limit, which prevents playing back sounds uncomfortable for the user. All these factors have to be taken into account when performing the test-retest analysis, and now I will briefly present you our approach. To begin with, we used a Jacoti database containing audiometry sessions from almost 10,000 users. And next we found that all consecutive test-retest session pairs originating from the same user. Next, we identified common frequencies in the test-retest session pairs. Based on these common frequencies, we analyzed the test-retest threshold deviation, and we eliminated bottom and ceiling thresholds. We computed threshold difference for each available frequency and average threshold difference across frequencies. Finally, we quantified the percentage of test-retest differences within a margin of 5 dB and 10 dB. Now, I will demonstrate the method based on one example of a test-retest session pair, which you can see here. This row represents 12 frequencies that can be measured with Jacoti audiometry test. Here you can see all thresholds that were measured in the first session, and here all thresholds measured in the second session. In this session pair, there are only 8 common frequencies, which you can see here. And for these 8 common frequencies, we compute the difference between the first and the second measurement. And some of these differences come from threshold values that are at the bottom or at the ceiling of the measurable scale. And these differences are excluded from the analysis, and the remaining values contribute to the overall statistics of threshold differences in individual frequencies, and to average threshold difference between 2 sessions. And with this approach, we analyze following conditions: 2 different test procedures available in Jacoti Hearing Center, full audiometry with 12 frequencies, and screening tests with 4 frequencies. And also we analyzed 2 different datasets, one consisting of all available session pairs, and the second one including only fully completed session pairs. In the table on the right, you can see also the number of session pairs and the number of total users from the database, which we analyzed in each condition. And now let's see this table presents the most important result, and here you can see what percentage of threshold differences lie within the margin of 5 dB and 10 dB. And as I mentioned before, this is computed for threshold differences in individual frequencies and also for average threshold difference. We can see that between 60 and 77% of threshold differences in individual frequencies and 72 to 86% of average threshold differences lie within the margin of 5 dB. Results for complete session pairs are better than for the incomplete session pairs, which means that the test is more reliable when performed by the users who were motivated to measure all frequencies. Now, looking at the 10 dB margin, we can see that between 81 and 90% of threshold differences in individual frequencies lie within that margin. And also between 86 and 89% of average threshold differences are less than 10 dB. And here again, results for complete session pairs are slightly better. So given these results, is smartphone-based audiometry of Jacoti Hearing Center as reliable as conventional audiometry? To answer this question, we can compare our results with the values for clinical audiometry from the literature. But we can only do this comparison for specific groups of participants who took part in these clinical studies. First group is the group of normal hearing participants. Based on several studies, in total 64 participants, we computed the weighted average for 5 different frequencies. We compared with 275 normal hearing participants of Jacoti audiometry, and we can see that depending on the frequency, Jacoti full audiometry is a bit more or a bit less reliable than clinical audiometry. But still, in all frequencies, majority of test-retest differences are in the margin of 5 dB. We also compared 217 Jacoti users with mild to moderate hearing loss with 32 participants of a clinical study who had either normal hearing or high-frequency hearing loss. And here again, the comparison depends on the frequency. And for low frequencies, Jacoti tends to be worse than clinical audiometry, but for high frequencies, it is better. And with this, we almost reached the end of this presentation, so now let me summarize what I talked about. At the beginning of this presentation, we argued that smartphone-based audiometry provides an alternative solution for hearing diagnostics, which has to be evaluated. To do this, we analyzed test-retest reliability of Jacoti Hearing Center iOS app based on real-life user data. We proposed methods for dealing with incomplete data and with bottom or ceiling effects. And our results showed that the majority of test-retest threshold differences lie within the margin of 5 dB. And this suggests that audiometry and screening tests provided by Jacoti Hearing Center are as reliable as clinical audiometry. And consequently, this hearing test can be integrated into a calibrated hearing device that also performs hearing loss compensation. And with this, I would like to thank you very much for watching this presentation and invite you to check more information about this study and about Jacoti products in general. Thanks a lot and have a nice day.